Welcome to our video on Directory Memory Access, commonly referred to as DMA. In this presentation, we will explore the fundamental concepts and functions of DMA, a crucial technology in modern computing systems. The data transfer instruction. The instruction move data in RO transfers data from an input-output device to a register in the processor. This can only happen when the device is ready. How the processor checks if the device is ready. In the polling method, the processor regularly checks a status flag to see if the device is ready. This involves running multiple instructions until the device responds. The second approach interrupts. The device sends a signal or interrupt request to the processor when it's ready. The processor can then stop what it is doing and handle the data transfer. Polling is simple but inefficient, while interrupts are more efficient but more complex. The choice between two depends on the specific needs of the system. In addition to the polling, the status register of the device, instructions are needed for incrementing the memory address and keeping track of the word count. When interrupts are used, there is an additional overhead associated with saving and restoring the program counter and other state information. To transfer a large block of data at high speed, an alternative approach is used. That is, a special control unit may be provided to allow the transfer of a block of data directly between an external device and the main memory without continuous intervention by the processor. This approach is called direct memory access. DMA transfers are performed by a control circuit that is part of the input-output device interface. This circuit is known as DMA controller. DMA controller perform the same function that would be normally carried out by the processor when accessing the main memory. For each data word transferred, DMA controller provides the memory address and all the bus signals that control the data transfer. DMA enables peripherals to handle data transfer directly without involving CPU, freeing it to perform other computations or tasks, which improves overall system performance. Especially for large blocks of data, DMA provides efficient data movement between memory and peripherals, significantly speeding up the process compared to the CPU managed data transfers. These advantages make DMA an essential feature in systems where performance and efficiency are crucial, such as embedded systems, video streaming, or data acquisition devices. A direct memory access controller is a crucial component in computer systems that allows certain hardware subsystems to access the main memory independently of the central processing unit. Here is a detailed overview of its functions, components, and benefits. Functions of a DMA controller. The DMA controller manages the transfer of data between input-output devices and memory without involving CPU, allowing for more efficient data handling. The different data transfer types are memory to memory, transfer data from one memory location to another. Input to memory, transfers data from an input device to memory. Memory to input output, transfers data from memory to an input output device. The DMA controller can manage multiple data channels, allowing it to handle several devices simultaneously. Bus arbitration, it controls the access to the system bus, deciding when a peripheral device can transfer data. Components of DMA controller are control logic manages the operation of the DMA controller and interfaces with the CPU and memory. Address register holds the starting address of the data in memory where the transfer will occur. Counter register stores the number of bytes to be transferred. Status register indicates status of the DMA operation. For example, ready, busy. DMA request line used by the peripherals to request DMA service. And finally, DMA acknowledgement line used by DMA controller to acknowledge the request from the peripheral device. Bus arbitration is essential in computer system to manage access to a shared bus among multiple devices. The two primary approaches to bus arbitration, centralized and distributed, each have distinct characteristics, advantages and disadvantages. In centralized bus arbitration, a single bus arbiter is responsible for controlling access to the bus. The arbiter decides which device gets access based on predefined criteria such as priority or record signals. Some of the characteristics of centralized arbitrations are single point of control. A dedicated arbiter manages bus access receiving requests from all devices. Priority management. The arbiter can implement priority scheme to determine which device gain access first, often based on fixed priority levels. The design and implementations are generally similar as all control logic is centralized in one unit. In distributed bus arbitration, each device participates in decision-making process for bus access. This approach allows devices to communicate with each other to determine which one will access the bus next. Some of the characteristics of distributed arbitrations are peer-to-peer control. Devices cooperate to resolve conflicts and determine which one gets to access the bus. Decentralized logic. There is no single arbiter. Instead, the logic for arbitration is spread among all devices. Thank you for watching.